Get started. Big class today. Right, so as I said in the message, I'm just pushing the schedule back by one day, by one class. So all the assignments have also been pushed back, and I believe I already changed those due dates, both on WebAssign and on Blackboard. The one exception is the last project, because that's going to be due the last day anyway, May 5th. So that's still going to be due May 5th. But everything else should be pushed back, and you should notice that. All right, we're looking at the properties of the trig functions, right? So just before we took the exam, we did right triangle trigonometry. That's where we left off, right? So we kind of already studied the trigonometric functions, what they are, how they're defined, but we didn't really study any of their properties, like what are their domain, the range, things along those lines. We're looking at that now, also looking at the graphs. Right now, here's the graph for sine, right? Remember, we did say that they were periodic functions. Now you're actually going to see what it means to be periodic. Right? This is one period from 0 to 2 pi. If you notice then, the pattern then repeats. So it's going to continue to look like this forever in both directions. And cosine, notice it actually is just the sine function that's shifted over. Right? Otherwise, the shape is exactly the same. Right? Except sine crosses at the origin, whereas cosine crosses up at 1. That's the only difference. For that reason, both of these are called sinusoidal. So these would be called sinusoidal curves. Right? Whenever you now hear the term sinusoidal, you should immediately think either sine or cosine. This is the shape.
So that's one period.
Only this, from the orange to the orange, that's one full period, 0 to 2 pi.
So there could be 4 periods.
Right, so if it was out to 4 periods, if you started here, it'd be from here to here, and then 3 more of those exact patterns. Right, this is more, the whole graph itself is more than 1 period. Right, because 0 to minus 2 pi is a period as well. So this is what looks like 2.5 periods on each one. Don't know if you've been in the hospital and you were hooked up, the heart, they call it sinus rhythm.
Yeah.
This is why heart rhythm is sinusoidal. There's a lot of other things that are sinusoidal. If you look at a pendulum, for instance, if you ignore friction, you push the pendulum and you just let it go, ignoring friction, it's going to be sinusoidal. Its motion just keeps going. Now, the reason that the clock pendulums keep going is because there actually is like an exerting force going. That's why you have to wind your clock, because it's using force to keep the pendulum going. But that's sinusoidal. Generally speaking, if you bounce a ball, again, ignoring the loss of energy, that's sinusoidal. And it'll go on forever. Now, this is still sinusoidal, it's just that the amplitude just keeps dropping, right? So that's all sinusoidal. Waves are sinusoidal. That's actually the most common example of sinusoidal functions. It's called a sinusoidal wave. And if you study physics, you study waves, it's all trig. Obviously, going with that, both periodic with a period of 2 pi. For both sine and cosine, their domain is all real numbers. Their range, -1 to 1. Sine, cosine never go below -1, never go above 1. They're always bounded by -1 and +1. Right, we already mentioned sine of x is odd, means it's symmetric about the origin. Cosine of x, cosine is even, so it's symmetric about the y-axis. Right, so really the only new thing here is the domain and range. Right? Everything else we've kind of looked at. Going to a real general sinusoidal function, A times sine of bx minus c plus d or cosine. Both will be sinusoidal. Properties. Period will be 2 pi over the absolute value of b. Right, so only sine of x is 2 pi periodic. When you have sine of bx, its period changes. And same with cosine, right? This holds for both sine and cosine. Amplitude is the absolute value of A. All right, this is the vertical height from the midline. The midline is, if I go back real quick. In this case, the midline is the origin. It's just kind of like, where's the center of the wave? So obviously, if there was a plus d, let's say it's plus 1, the midline shifts up 1 unit. So midline would then be 1. The amplitude is the height off of that. And height, it's really a sine height. Plus 1, minus 1. This is a height that's down 1 unit. So that is your amplitude. Phase shift, we just call it the horizontal displacement. Right, so obviously, it's going to be horizontal displacement minus c, but you have to factor out the v first. So c over v is your horizontal displacement, and we call that, when we give us sinusoidal functions, a phase shift. Just a fancy term. But that's nothing new. We've worked with that before. Right? Horizontal shift doesn't get a fancy name because no one cares about it. D. Then your line y equals d becomes the midline.
And we're going to be using this.
Yes. You may see some applications with it. Most part for us, it's going to be, we might give you a sinusoidal function and say what's its amplitude, right? What's the phase shift, graph it, things like that. If you take any kind of applied mathematics and engineering, physics, anything electrical, also deals with sinusoidal waves, you'll be dealing with these functions a lot. Anything that deals with waves, you'll be dealing with sinusoidal. Remember, light is a wave. Light's both particle and wave, so even light can follow this. If you're looking for the sign, it's just right up there. All right, so that's sine, cosine. Tangent. This is the graph of your tangent function. This is the shape here. Right, so notice for graph, we're going to go minus pi over 2 to pi over 2 to get the full context. And it is periodic, just like sine and cosine. So this pattern repeats forever, both ways. So consider a general tangent function A, tangent of bx minus c plus d. We're going to call an amplitude now, right? Because, unlike sine and cosine, notice, it doesn't have a max or a min. Right, so we can't call it amplitude. So what we do is we just call the stretching factor, and it's the absolute value of A. Period, same kind of thing, pi over the absolute value of b, because tangent itself is pi periodic. Obviously, if you're not going to multiply your x by something, that changes. Domain is the set of all real numbers except those of this form. Just sine over cosine, right? It's going to be 0, or it's going to be undefined wherever your cosine is 0. If you're looking at just the tangent of x, its domain, everything except odd multiples of pi over 2. That's just a tangent of x. However, range, all the numbers. So unlike sine and cosine, where you can only get -1 to +1, tangent, you can get everything out of it. Again, tangent is, it's not really rational, right? Because rational is a polynomial, but it's rational-like. It's a fraction. It's going to have vertical asymptotes wherever the denominator is 0, which is, of course, whenever cosine is 0. So wherever the exclusion points are from the domain, those are all vertical asymptotes. There's an infinite number of them. Obviously, there's no amplitude. Secant and cosecant. Here is the graph for secant, along with cosine. Right, notice what's happening with secant. They're kind of parabolic, and again, there's an infinite number of them. Notice where the vertex is, though. The vertex occurs at each maximum of cosine. And cosecant, again, it's the exact same secant, just shifted. And has the exact same property. They're all kind of parabolic, with the vertex occurring at the max or min of something. Starting with secant, once again, it's not going to have an amplitude. We just call obstruction factor absolute value of A. Period 2 pi over the absolute value of B, the exact same as cosine. It is going to have a restricted domain. All real numbers except those where cosine is 0, which is, by the way, the exact same as tangent. So its domain is the same as tangent. Range, minus infinity to negative absolute value of A plus D, union with absolute value of A plus D to infinity. That accounts for all the translations.
These slides will be posted, right?
Just like tangent, vertical asymptote, every time cosine is 0, so every of those exclusion points in the domain, they have vertical asymptote. And remember, there's an infinite number of them because it's periodic. And once again, there's no amplitude. In fact, the only two trig functions that have an amplitude are sine and cosine. Because of how similar sine and cosine are, secant and cosecant are also very similar. So a lot of these features of cosecant are the same. Stretching factor absolute value of A, period 2 pi over absolute value of B. Domain, now everything except when sine is 0. And so not equal to C over B plus pi over absolute value of B times K, where K is an integer. If you're just looking at cosecant of x, Domain is all real numbers except multiples of pi. Right, because every multiple of pi makes sine 0. The range is the same as secant. So for both secant and cosecant, if you're just looking at secant and cosecant of x, the range is everything except -1 to +1. Because you're taking the reciprocal of the sine and cosine. Right? Has an infinite number of vertical asymptotes at each of the exclusion points of the domain. And no amplitude. And here's cotangent.
And is that like, you said that's infinite? Like it just keeps going? Like just
Because it's periodic.
Okay.
Right, so 1 period is pi. Minus pi to 0 is 1 period. 0 to pi is a period. Right, so if really you can look at, this is the shape.
Mhm.
And then it just repeats every period. Stretching factor, absolute value of A, again, doesn't have an amplitude, right? Period pi over the absolute value of B, remember both tangent and cotangent are pi periodic. The domain is the same as cosecant. Right? Because cotangent is cosine over sine. Cosecant is 1 over sine, so they have the same domain. The range is everything. Once again, you're going to have vertical asymptotes at every exclusion point, so once again, same as cosecant, and no amplitude. So sketching graphs over one full period. Each of the vertical lines represents pi over 2. Each of the horizontal is going to represent 1. X scale is pi over 2, Y scale is 1. Now they only want one full period. How we do that is our business.
Sine is like the one in between, right? So it's like the one that only takes up like the middle period.
What do you mean takes up the middle?
Like it's the one that goes in between like the big one, right? You know?
What do you mean big one?
I don't know the name of it. What's the one that goes in between? You got the notes, right?
Start with the midline. Y equals 0.
Amplitude is 3. Also, it goes up to
Amplitude will be 3.
Yeah.
So as a maximum of positive 3, a minimum of negative 3.
Oh, that's what I meant. It goes to a max or minimum of like the cotangent or whatever it is. Right?
Cotangent doesn't have a max or minimum.
I'm into the one with the like that looked like a.
Secant, cosecant also not max or minimum. Period 2 pi, it's just sine of x, right? Now we just have to decide how do we want to do our full period. We could go 0 to 2 pi. Right, but we can choose any interval that's 2 pi in length. Why not go minus pi to pi? It kind of balances on both sides. That would be minus pi there. That's positive pi. I'm just going to sketch it over that interval. Now, where is sine equal to 0? Every multiple of pi. 0 there, 0 there, 0 there. At pi over 2 is the maximum. Here's pi over 2, 1, 2, 3. So it's going to go up to positive 3 there. Negative pi over 2 results in a minimum. So negative 3. And then you just have to reproduce the sinusoidal wave.
It's kind of interesting because in like engineering, we measure like frequencies with sine waves. And stuff.
I mean, you're measuring the frequency of a wave.
Yeah, 'cause
And all waves are sinusoidal.
yeah, that's what I mean. Like,
Frequency is one of the period. If I remember correctly, the frequency is in hertz.
Yeah.
Periods typically in seconds. No, looks good enough. Sine of 2x. Midline, once again, is the x-axis. And has no vertical.
Amplitude is 0 or 1.
Amplitude is 1.
Period is 2x. Over pi.
2 pi divided by the absolute value of what x is being multiplied by. This gives you a period is pi. One full period would be a length of pi. We're going to try and stay balanced. That'd be minus pi over 2 pi over 2. It's going to be 0 at minus pi over 2, the origin, and pi over 2. Let's say this is pi over 4 here. Have an amplitude of positive 1 at pi over 4. Negative pi over 4 will be down at negative 1. Equals sine 2x. Notice it's squished, right?
That's the one that goes in the middle of them, right? You showed us that one slide with the graph, okay? And it was like the sign was like this one squished one in the middle, and then you had the big ones that were.
Those are secants and cosecants. For sine, it was cosecant. And that wasn't squished, it was just there to kind of show you how they're related. I mean, this is a vertical compression by a factor of 2, right? Remember all the way back when we did the transformations? Four times sine of x over 2. And so there's no movement along the y-axis. So the midline is still the x-axis, y equals 0.
Amplitude is 4.
Amplitude equals 4, the period. And I might start doing this.
With pi over 2.
Capital A for amplitude and capital T for period. X is being multiplied by 1/2. Period is 2 pi over 1/2, which is 4 pi.
So it's just 2 pi over
What X is being multiplied by. Well, technically, it's the absolute value of what X is
I
being
didn't
multiplied by.
I didn't know that you could have the fractional in the fraction like that.
You're allowed to divide by a fraction, right? Dividing by 1/2 is the same as multiplying by 2. I'm going to need the entire x-axis in this case. And then the 4 pi would be minus 2 pi to 2 pi. 0 at the endpoints and right on the y-axis. Normally we then look at minus pi over 2 and positive pi over 2, but we need to double those now. So minus pi and positive pi is what we're looking at. Pi will result in a max. Minus pi results in a min. So we go down to -4 at negative pi and up to +4 at pi. We have to sketch out our sine wave. And say there's 4 sine of x over 2. Four times cosine midline y equals 0.
Amplitude is 4.
Amplitude is 4, period is 2 pi. I want to be balanced. Again, I'll go minus pi to pi. Maximum occurs at 0. Minima occur at your two endpoints. And an odd multiples of pi over 2, it's 0. It would look like that if that's the interval we decide to use. That doesn't really look like a wave.
Can't you just put another dot on the other side and just continue it up?
That'd be more than one full period then. So maybe choose a different interval. I don't know, we could go minus pi over 2 to 3 pi over 2, if we wanted to. Maybe 0 there. 0 there and 0 there. Remember, every odd multiple of pi over 2, you get a 0 for cosine of x. Minus pi over 2, and 3 pi over 2, all zeros. Cosine of 0 is a maximum. Cosine of pi would be your minimum. That kind of looks more like a wave. Doesn't matter how you do it. As long as you graph one full period, you're fine. What interval you choose doesn't matter. I'll do this. I'll include the intervals that I used as well for those. So it doesn't matter. My opinion, the green one kind of shows off more, makes it actually look like a wave. But you're not incorrect if you do minus pi to pi. Or 0 to 2 pi even, if you want to do that. Midline still y equals 0, the x-axis. Amplitude now is 2. Period.
Is 2 pi over 1/3.
Period is now 6 pi over here. My coordinate system isn't large enough to handle that. That means what I'm going to have to do is I'll come up with a new coordinate system. I think I will show this all. Just for those who are interested. It's going to plot over minus 3 pi to 2 pi. So I'm going to add two things here. I actually want to change that. And that gets you my grid. Now, just if you're interested in how I get the grids. I will need the whole coordinate system. Minus 3 pi, positive 3 pi, which means I'm not going to get that wave feature. If I want to do that, I have to change my coordinate system up, and not that big of a deal. Maximum still occurs at 0. Goes up to 2. The minimum still occur at the two endpoints. -2 there and -2 there. It's 0 generally at odd multiples of pi over 2. Right, so negative pi over 2 would be a 0, but we have to multiply that by 3. Negative 3 pi over 2 is the 0. And then it was pi over 2, multiply that by 3. 3 pi over 2.
Why are you doing that? To get what?
It's where it's 0. It's where cosine is equal to 0. Just so I have some points to plot. Something like that. And if I go back to my transformations, this has two stretches. Right, it has the vertical stretch by a factor of 2 and a horizontal stretch by a factor of 3. Really makes the stretching easier to see when you only look at a restricted interval, right? That would have been minus pi to pi, but we stretched it by a factor of 3, the minus 3 pi to positive 3 pi. And normally we only go minus 1 to positive 1, but we stretched it by a factor of 2, right? So now it went minus 2 to positive 2. So tying everything together. Okay, we're out of the sinusoidal functions. Oh, I don't want you to do that. Come back up to user. Tangent has no midline, so don't worry about that. It doesn't have an amplitude.
The amplitude wouldn't be 2.
Because tangent doesn't have a max or nor a min. Instead, we call it the stretching factor. Again, it should be equals. We have a stretch factor of 2. It does have a period. Pi. We also get vertical asymptotes now. In one full period, we're going to have 2 of them. Now you have to decide what interval do you want to sketch over, right? For tangent, the standard is minus pi over 2 to positive pi over 2, because that gets you a full picture. Those would be my 2 vertical asymptotes in that interval. The 2 endpoints would be our asymptotes. Remember, it's every odd multiple of pi over 2 for tangent is an asymptote. There we go. Tangent of 0 is 0. And this way you have to know how the tangent behaves. On the left side of a vertical asymptote, it increases to infinity. On the right side of a vertical asymptote, it decreases to negative infinity. So we'll start from down here. It'll come up from down here, We'll have to cross through the origin and then goes up on that side. But we also have to take into account the stretching factor of 2, which is annoying. Halfway. Right, negative pi over 4 and pi over 4. At pi over 4, isn't tangent 1? So tangent of pi over 4 is 1, right? But that gets doubled because of the stretching factor. So I'm going to pass through that point. Tangent of negative pi over 4 is negative 1. That has to get doubled because of the stretching factor. So we're going to have to pass through that point as well. Something like that. And be careful, because unlike the cubic, does something like this. For a brief instant, it does go fully horizontal at the origin. Tangent doesn't. Tangent never goes horizontal. Right, so be careful when you're sketching it. It's not exactly the cubic function. You can actually see more why it's like that in calculus when you look at derivatives and slopes at a point. In fact, that slope should be 1 at the origin. So it should look like the line y equals x. Oh boy. Tangent of 2x. Stretching factor is 1. It actually doesn't have a stretch factor here, right? I'll just write it out. No midline. We do have a period. What's the period here? Pi over 2. Which is another, it's going to be a pain. And we do have vertical asymptotes. You again need to decide what interval you want to sketch over. The standard interval for this would probably be minus pi over 4 to positive pi over 4. Your endpoints will once again be the asymptotes. Right? There's normally be what? Every odd multiple of pi over 2 would be an asymptote, right? So you have negative pi over 2 as an asymptote, but you now have to multiply that by 1/2 because of the period. So now it's negative pi over 4 as an asymptote. Pi over 2 would be an asymptote, but you have to multiply that by 1/2. Now pi over 4 is an asymptote.
So you gotta multiply the period by 1/2. to get your vertical asymptote?
No, I'm not multiplying the period by 1/2. I'm multiplying the actual asymptotes themselves by 1/2. And basically, every point you plug into tangent now, multiply by 1/2. Because you're multiplying by 2, makes 2x. So if you still want tangent of pi over 2, well, let's plug in for x. Pi over 4. Just 2 times pi over 4 is pi over 2. That's really what I'm doing.
Okay.
So before I use that, negative pi over pi over 4 is going to be halfway between pi over 2 and 0, right? That looks like halfway. So those would be the two endpoints. Notice how small this interval is going to be. Like I said, it makes this one fun. There's an asymptote. There's an asymptote. Still crossing the origin, 0, 0. Just going to plot 2 more points. For the other tangent function, I used pi over 4 minus pi over 4, right? Because of those 2 points, tangent is plus and minus 1. Then I multiply it by the stretching factor. Now in this case, stretching factor is 1. But remember, we have a period pi over 2, because we're multiplying by 2x. So instead of pi over 4, I'm going to be using pi over 8. And tangent is 1 at that. Tangent of 2x is 1 at that point. Pi over 4 divided by 2. Right, 2 times pi over 8, pi over 4. Well, then it's going to be about halfway between the asymptote and the origin. I don't know, maybe like right about there. It'll be pi over 8. Tangent is equal to 1 at that point. That would probably be minus pi over 8 there. Tangent would be negative 1. And then the behavior is still the same. On the right-hand side of the asymptote, it goes down to minus infinity. Right, so we're going to be starting down here and coming up. Left-hand side of the asymptote goes up to positive infinity, right? So it's going to have to end going up that way. I'm going to have to do something like that, I guess. Again, being careful that through the origin you don't make it horizontal. Try and keep it similar to y equals x. Now kind of be like tangent of 2x. And remember, this pattern does repeat, right? So I could extend out to here. Pi over 2 would now be another vertical asymptote, and between these two lines, you'd have this exact shape again. And that would continue on forever in both directions. So if you want a full picture of tangent of 2x, that's what it would be. Which is why generally we just want one full period. Right? If we know what one full period does, we know the whole thing does because it just repeats. Okay, sine of x plus 3, back to sinusoidal. All right, back to sinusoidal, which means we have a midpoint.
0.
Not for this one.
3.
This one's going to be 3. The midpoint here is 3, right? Because what does this 3 represent? A translation in the vertical direction, right? So the midline originally is here, but the whole thing gets translated up 3 units. There's your new midline. Does that make sense? What I'm going to do is shift the coordinate system as well. I'm actually going to draw.
You're on the right web line.
I'll actually draw my midline. And I'm going to treat that now as the x-axis. Which means we can now ignore this bit here. Now just look at sine of x and focus on that. Amplitude. What's the amplitude of sine?
2p.
2p.
No, 2 pi over.
You give me period. What's the amplitude?
0. 1, I mean.
1.
Oh, 1.
Remember, amplitude is height off the midline.
Yeah.
Period.
It's 2 pi.
In this case, just 2 pi, right? Because it's 1 times x. So everything else is the same except the midpoint shifted. Or the midline shifted. Pick an interval. Again, let's go minus pi to pi. There's negative pi. There's pi. Right, so in a sense, kind of draw the points there, right? Sine is 0 every multiple of pi. Remember, when I say 0, I really mean my midline. The amplitude says how high we're going, right? Or how low. At positive pi over 2, sine is 1, right? Sine pi over 2 is 1. So I have to go 1 unit above the midline on that for it. At minus pi over 2, I have to go 1 unit below the midline, so I'd be at 2. So it probably looks something like that. Now dy of sine x, y equals sine of x plus 3. And if you wanted to, you could erase the midline. Just go look, say I didn't do that at all. And then I erase those as well, probably. Oh, that's right. Speaking of waves, that's actually your last project. Your last project is on waves. I don't think it posts till next week, if I remember correctly. It will post on Wednesday or next Monday. Cosine x minus 2. Maybe it's actually already posted. I don't know. Sinusoidal, so we have a midline. What's the midline here?
0. -2.
In this case, it's -2. Because it's cosine of x minus 2. Let's go ahead and make that. Oops. What's the amplitude?
1.
Hmm?
1.
Amplitude is 1. What's the period?
2
And again, we're going to have to choose an interval. We're going to do negative pi over 2 to 3 pi over 2 again. Get the full wave effect. So I'll start here, negative pi over 2. And we'll go out to positive 3 pi over 2. Well, every odd multiple of pi over 2, cosine is 0. Negative pi over 2 will be on the midline, positive pi over 2 will be on the midline, and positive 3 pi over 2 will be on the midline. Cosine of 0 is 1, right? So we go 1 unit up from the midline. Cosine of pi is -1. We go 1 unit down from the midline. That looks terrible. Looks a little better. Curve. And we're gonna have something like that. Sinusoidal. What is the midline here?
Really fine. And mine is on power 4. Negative power 4.
Now, pi over 4 is important, but it's not for the midline.
0.
Yep.
1. Because it's in parentheses.
Well, yeah, because that minus pi over 4 is in parentheses, right? That's minus pi over 4. Right, so we have no translations in the vertical direction, right? What's our amplitude?
Negative pi, 2 pi over 4. Not 1.
It's just 1. What's our period?
2 pi over 4.
Just 2 pi. The x isn't being multiplied by anything, right? Technically, it's being multiplied by 1.
Oh, is that going to be like...
But that minus pi over 4 is important. It does play a role. That is called the phase shift.
We have those two.
And we typically represent phase shift with a phi. Phase shift is pi over 4. And for this one, I'll put in parentheses that is the phase shift.
Because we have those as well in engineering, like when reading frequencies and stuff, and that's like, it's either like lagging or leading another frequency.
All it really is it's a translation in the horizontal direction. We're dealing with sine. Normally we'd be minus pi over 4 to pi over, minus pi to pi, right? Let me actually do those in green. That's typically where we would start. But we have a phase shift now of pi over 4.
You just move it over. Or move it back since it's negative. And
Your first time. A positive phase shift is to the right. I'm sorry. Yeah, to the right. And the phase shift here is positive because it's subtraction. Remember, it was sine of bx minus c, and then plus d, where c is your phase shift. Oh, I'm sorry, c over d is your phase shift. In this case, b is 1. So I'm going to do a lot of stuff in green as well, and then I'll erase it. Sine is 0 at every multiple of pi. That would have been there, there, and there, right? But we have a phase shift. So it's there, there, and there now. Where is sine negative 1 in this interval? Start with the green interval, minus pi to pi.
you said where's the phase shift in the green one?
We're sine negative 1 in the green interval, which is minus pi to pi. So sine of what is negative 1?
Negative 1. 2,
That's what's positive 1,
negative pi over 2.
negative pi over 2. Which is right here. Goes down to negative 1 there. But we have a phase shift.
So it goes to black.
Right, so it goes over by pi over 4. And here's pi over 2.
Wait, so the green is the original one?
Yes. All right, so I'm doing it in green just to show you my kind of like my thought process.
Okay.
And then phase shift it over. And now before I actually sketch to remove all the confusions, I'll get rid of these. And now it's just a standard sine wave. Although I really should be careful and decide. At 0, where should I be crossing the y-axis? Being negative root 2 over 2.
In the middle of it?
Well, it's not going to be right in the middle. Negative root 2 over 2. Split what? 1, negative 1.4 over 2. So that would be what? Slightly below 1/2? Negative 1/2? That was good. So maybe something like that. And then maybe on a quiz or a test, just tell me what interval you're sketching over, just so I have it for comparison. And I've been saying what we're sketching over, so I'm not really writing it down, but just let me know what interval you're using. You can even just
Write a graph?
write it on here, right? Say this is minus pi over 4. I'm sorry, not pi over 4. That'd be negative 3 pi over 4. That'd be positive 3 pi over 4. You could also just write those points there, just so that I have a reference so I know what you're sketching over. Cosine of x plus pi over 6. This one will be rough. What is our midline?
Midline is going to be 0. The amplitude is going to be 1. The period is going to be 2 pi. And the phase shift is going to be pi over 6. Negative pi over 6.
Phase shift here is negative pi over 6.
So it's going to be moving to the
0 moving to the left. Again, I'll start with the green. I'll worry about the phase shift later. So I'm going to start with assuming it's just cosine of x. Pick an interval. What have we been doing? Negative pi over 2 to 3 pi over 2? There's negative pi over 2. That would be 3 pi over 2 there. Every odd multiple pi over 2, cosine is 0. Cosine of negative pi over 2 is 0. Cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. At 0, cosine is 1. At pi, cosine is negative 1. Now let's deal with the phase shift. We're moving to the left by pi over 6. It is not quite halfway. It's not going to be halfway between here. It's going to be more closer to the original point. So I don't know, maybe somewhere there. Something like that. And I have to do the same argument here, so maybe something like that. And we're going to have to move every single point over by pi over 6. Maybe there. Maybe there. There. Does that kind of look like to the left by pi over 6? Something like that. And then I'll just get rid of those points. It's coming up. Well, that looks terrible, actually. That looks better. Where's it going to cross? What is cosine of pi over 6? From the unit circle, cosine of pi over 6.
As a degree.
Pi over 6 is in radians, but the output isn't radians or degree.
Can I guess one?
Exact value.
What are those 3 over 2?
Yep, root 3 over 2. And so, then we'll print out that one slide that had the unit circle on it, and just keep it in your notes. Because we will be referencing the unit circle a lot. Unless you have it memorized, which I doubt you have. Oh, he has apparently. So that's how you memorize, bro. That's brownie points.
Or did you pull it out of the test? I would pull it out the
That's brownie points right there.
test.
Root 3 over 2. Root 3 is, what is it? It's like 1.7? 1.8, somewhere around there. So it's going to be a lot higher up than root 2 over 2 would be. But not quite 1, so it should probably cross maybe right about there. That would look good. That. And maybe looks something like cosine of x plus pi over 6. I didn't have anything here about secant, cotangent, even though it's actually really hard to find sketching problems on those for some reason. But the general process would be the same. Right? Know the general shapes, which I gave you at the very start, and then follow this general process. Remember, only sine and cosine will have an amplitude in the midline. Everything else doesn't. The other three, so those secant, cosine, cotangent, would go more along the lines of what we did for tangent. And then what I tried to do was break it down. Instead of doing like all of it in one problem, I kind of broke it down where we just looked at how does the amplitude affect it, then how does having a midline affect it, and then how does having a phase shift affect it. You have to combine those all together if you get something that has all of them. But again, the procedure is the same. So I would always recommend start with breaking down your information. Midline, if you have one, amplitude or stretching factor, depending on what function you're working with. Your period, and your phase shift. Write all that information down first, and then start sketching from there. Are there any questions on the properties of the trig functions? Notice I'm calling them properties, not identities. These are just the general properties. We'll be looking at identities actually very soon.
Are we gonna have to do, no, not we're gonna have to do, are we gonna go over like secant and stuff for them?
Well, I did the graphs. I showed what they look like. But I don't have anything in sketching.
Okay.
Because it's really difficult to find problems like that.
All right.
It's just generally speaking, we work with sine and cosine
So,
in applications.
and like sometimes tangent or something?
Very rarely.
Really? So on the test, we would be like, if there was a question that told us to sketch a graph, it would be like.
I could throw a secant on there. Because remember, the test also takes what we did in class and is supposed to expand. Some questions on there will expand what we did. But it's the same procedure. Just know the shapes. Know your general shapes. Determine your period. For secant and cosecant, you won't have to worry about midline. Right? So determine your stretching factor. Determine your period, and determine if there's a phase shift. And then sketch from there. And so one full period here makes it tough. And if you wanted to go minus pi to pi, right? You'd only have this half here, this half here, and then the entire middle. You're never going to be able to do in one full period both of those.
You can't do negative pi over 2 to...
Oh, actually, you could go, what, negative?
I was going to do negative pi.
You could, yeah, I'm sorry. Negative pi to 2 to 3 pi to 2 would work. Yeah, that one would work. That one would work. So you'd be able to get that and that. That's probably what I'd use for secant. For cosecant, yeah, do like minus pi pi. Right, and then you get both of those. Those would probably be your best choices, right? For something like secant and cosecant. But the procedure itself is the same as what we've been doing. It's just different shapes. Again, the biggest application of this kind of stuff is, as you were saying, engineer, when you're working with waves. It's always going to be either sine or cosine in that case.
Could we have like that stuff too, like the amplitude, like period and stuff? We have to measure that, like when looking. You know what like a oscilloscope is? Or no?
Probably, I just don't know its name.
Well, like it's just like.
Because we had to do that in my physics courses.
Yeah.
Remember looking at waves, sound waves, things like that we had to do, and we had to measure all that kind of stuff. Although when I did my advanced lab, I was working with lasers. And we had to do it with the laser beam, because remember, light is both a wave and a particle, so we had to examine in terms of both.
It's like we had like phase shifts, but like we put them in more in terms of like degrees than radians, like say like in like an inductive like circuit or something.
Well, yeah, you're doing circuits, so you're dealing with the
like we just
electric waves.
Yeah, we just look at like how much the voltage.
But it's the same thing.
The phase shift between like voltage and the current or something like that.
The exact same thing.
Yeah.
All waves behave the same, it's just the type of wave that they are. That's the beautiful thing about waves in physics, is they're essentially all the same. Right? Going from a light wave to a sound wave, there's no difference in the analysis because it's still a wave. Which means if you can analyze those, you can also analyze waves in the ocean, because it behaves the exact same way, because it's still a wave. It's really cool. So yeah, you're working with electromagnetic waves. Yeah, and that's why there's a heavy focus on sine cosine. That's where this stuff comes in. So when you analyze waves, are all sinusoidal. And again, that's what the project is. It's about, I think it's ocean waves. But it's based, of course, it's sinusoidal, so.
Yeah.
And we were actually, I think the project's going to have you analyze what happens when waves interfere with each other. So you're going to need some trig identities that we'll start covering to fully complete it. But it is really cool. Light waves is the only time that differs. Light waves don't really combine nicely. It's really weird. And I remember we also did in my physics, we did the, you can order the double slit. You shoot a beam of light, has two slits.
Oh, and like change.
And you analyze what happens.
Okay.
If it's a particle, you expect something different. Or I think it was if it's a wave, you expect something different. But it turns out that you get like the exact same pattern, like it goes through each slit equally, which is wave-like. It's so cool. How it works is so cool.
Yeah.
We also shot a laser through an atom
Really?
and got that diffraction pattern, which proves it's particle, which proves it has particle-like properties. Double slit is the wave-like properties, the shooting it through a nucleus is particle-like. And it's a specific diffraction pattern. Each atom has its own diffraction pattern.
You did that in college?
Yeah. But again, that was advanced. We did that more on the advanced side. And we actually analyzed that in my quantum class.
Quantum mechanics? So you talk about like Ant-Man and stuff? Like the quantum realm?
Oh, Ant-Man isn't quantum. Ants are actually Goliaths when you put them into the quantum scale. I don't think you understand how small the quantum scale really is.
Yeah.
Even ants are massive.
Yeah, because
Relative to the quantum scale.
because they made what's it called, like the quantum mania, and he goes into the quantum realm.
I'm not familiar with that, but the quantum realm is really weird.
Yeah, you gotta watch.
You don't want to delve into it.
Yeah, because he like shrinks himself so small until like then gets lost in the quantum realm.
So you don't want to. Unless you really want to get into physics, you don't want to study anything quantum related. It's just a whole different world. It's so weird. We just accept that it works. Because we haven't been able to find any counterexamples yet. And we're just like, yeah, it works. Okay, let's accept it. Move on with our lives and just worry about the math. It's not worry about why it works, we just accept that it works and move on. The homework on this stuff should be due the 21st. And let's actually check and see if project 4 is off. Let's check that real quick.
That's not live. No, he did. You live a liar, bro. Nah, you looked it up.
When I take away those brownie points, we look it up.
No, look at his smile. He looked it up.
No. No way you remember that. This is the only one I remember.
Is that one more on the thing?
Yeah.
Yeah, so the 4th project is up. Went up April 9th. And that'll be due May 5th, which is our very last meeting day, by the way.
All right, okay.
May 5th is our very last meeting day. Today, Monday. So we're going to look at, I think Wednesday is inverse trig functions. So we're looking at the inverse trig functions on Wednesday. See you all then.